So welcome to week number 10, and today we will be studying two new single qubit gates, which are T and T-Dagger Gate. Again, these two gates are the special cases for the phase gate, and today we will be also visualizing one quantum computing identity using this little tool of ours, the quantum glasses. So let's get to it. Again, since both of these gates are the special cases for phase gate, we need Hadamard gate to visualize the effect. Let's do this. So the T represents the T gate, obviously. Visualize it. So first again, the effect will be of the Hadamard. And again, if you want this tool, check out the first video in this playlist. So the first video will help you to understand what this playlist is all about. And again, it will help you to get this little GUI app for yourself. So Hadamard, we have reached here, and now we will see the effect of the T gate. You can see the color was changed, and you can see a little T over here, and it is moving slowly indeed. But so last time we saw S gate, and it had an rotation for pi by 2. So let's see what's the case for this one. And you can see it has stopped moving. So this is, if I show you, this is a pi by 4 rotation. All right. So for T gate, the value for lambda is pi by 4. And now let's get to the T-Dagger gate. Again, first Hadamard, then T-Dagger, and now visualize. Again, we know that the Hadamard will bring the state vector in this plus sketch state, but the superposition state, but then let's see what's the effect of it. And if you have seen the last week's video, you should be having a rough guess ready in your mind. And if that's so, pause the video right now and try to figure it out. So now you can see the color was changed, and you can see TDG written here, which is just represents the T dagger, and as you can see, it has moved in the opposite direction. The T gate moved the state vector in this direction towards Y here, and the T dagger has moved it in the opposite direction. And yeah, it has stopped. And if you see over here from the top view, you can see it's a rotation by a minus pi by 4 angle. Okay, so the value for lambda for the T-Dagger gate case is lambda equal to minus pi by 4. So now again, let's visualize the identity. So just like the last week, the identity is that if you apply T-gate and T-Dagger gate together, they cancel each other out. Okay, so both of them together are just as good as identity metrics. So let's just try to visualize that. So first Hadamard gate, then T-gate, and then T-Dagger gate, and let's visualize. Again, the first is the Hadamard gate. It will just bring the state vector here in the equal superposition states, the plus sketch state, and what's important is like what would happen later on. And if you've seen last week's video, I think you should try to guess. Pause the video right now and just try to guess what would happen. So the T effect has started, the T gate. You can see a little T written over here, and the state vector is moving to the very expected direction, what we saw for the T gate visualization. And now we will shortly see. Yeah, you can see that there was a slight change in color, but that there was one. And you can see T dagger written over here, TDG, which represents the T dagger, and it is dragging back the state vector in the opposite direction, and it has stopped here. So that's the visualization part. And if you notice that this state was nothing but the effect of the Hadamard gate. All right. But what happened is that even though we applied these two gates, the T gate and the T-Dagger gate, there was actually no change. All right. It moved in here and there, but ultimately it just ended up there where it would have ended up even after the application of the Hadamard gate. So these two gates, T and T-Dagger, actually had no effect. And that's what the identity is. All right. So now you've visually seen everything. So now let's get into the mathematics, and it's complex this time. It's genuinely complex. So let's visualize the identity, and as well as I will tell you the matrices that represent these two gates. So let's do it. So let's get to the mathematical part now. So let's first try to understand the T gate. So this is the symbol and this is the matrix. Again, we have T gate as a special case for the phase gate where lambda equals pi by 4, and we just substitute the lambda's value and the matrix for the phase gate, and we get this. And if we just calculate the value for e to the power I by 4, what we get is this. So this is what represents the matrix for the T gate. And again, let's quickly go to the T-Dagger gate, and you can see this is the symbol for T-Dagger, and you can just notice this a little dagger here. It's not a prime, it's a dagger. And this is the matrix, but the only difference is this minus sign between the T-Dagger and T-gate. So the value for T-Dagger gate is minus pi by 4, and again if you do the same thing, you get the matrix for T-Dagger, which is this. So the only difference is this minus sign. All right. So now let's get to the identity that we have already visualized and see how it works out. Okay, so we have T and T-Dagger. So what we just simply do is just substitute their respective matrices. All right, and then what you get is this. So let me explain what just happened here. So if you just try to calculate this normal matrix multiplication, you simply get all these three values. No, very simple. But for this fourth value, you need to multiply these two. All right. So for time being, let's call that result k, and let's try to solve by multiplying these two matrices. All right. So this is what the result is. So just notice at the end we will get 1 as the value for k. So let's try to work through it. As I just told you, the value for k is nothing but the multiplication of these two. So this root by root over 2 and this root 2 come together to make this 2, and then we just multiply the two numerators, and it is just the a plus b into a minus b, so it's a square minus b square, as you can see here. But recall that I square is nothing but minus 1, so we just substitute it here. So 1 minus of minus 1 becomes 1 plus 1, which is nothing but 2, and 2 by 2 is nothing but 1. So that's a simple explanation for how you get the value of k to be 1, and I just covered it because it involved this complex numbers, and it was a little bit more complicated than most of the stuff that we have seen previously. So now let's substitute the value for k, and if you observe this really carefully, this matrix, it's nothing but identity matrix again. So it's clear again that when you apply these two matrices together, their effect is just as good as identity matrix, and there is no effect for identity matrix. So I think that's it from this week, and then the next week we will be visualizing some more quantum computing identities using quantum glasses, and until then, take care.